Okay, let's dive right in. Have you ever wondered how a shiny nail turns into that crusty red rust? Or how bread dough just magically puffs up in the oven? Well, it's not magic, it's chemistry. And today we're going to crack the secret code that scientists use to describe all these amazing changes.
So here's our game plan. First, we'll see how chemistry is literally happening all around us. Then, we'll learn the secret language, the shorthand that scientists use. After that, we're covering the golden rule, balancing equations. We'll take a quick look at different reaction types, and then, you guessed it, we'll test out your new skills with a pop quiz. Ready? Let's do this.
All right, first things first. Chemistry isn't just for people in white lab coats, you know? It's happening in your kitchen, in your backyard, and yeah, even inside your own body right this second. It's the science of change, pure and simple.
So, I've got a question for you. Think about all these different things you see happening every day. What's the one thing that connects all of them? Just take a second and think about it.
If you guessed that they're all chemical reactions, you are 100% correct. In every single one of these examples, the original stuff, the milk, the iron, the food, is actually changing its identity and turning into something brand new. And that, in a nutshell, is a chemical reaction.
Now, trying to describe all these changes with words can get, well, a little long-winded. So scientists, being the efficient people they are, needed a faster, more universal way to talk about this stuff. Kind of like a secret code. Let's see how they turn a whole sentence into just a few symbols. You could, of course, describe a reaction in a full sentence like this one. It's totally clear, but can you imagine writing that out over and over again in your lab notebook? Yeah, no thanks. It's just way too long.
So the first step to making things simpler is a word equation. This is way better, right? It clearly shows our starting ingredients on the left and what we end up with on the right. Simple, clean, gets right to the point.
And here it is. This is the pro-level stuff, the universal secret code. By using chemical symbols, anyone, anywhere in the world can look at this and know exactly what's happening. No translator needed. It's short, it's precise, it's the language of chemistry.
Okay, let's lock in some key terms here. On the left side of that arrow, we have the reactants. Think of them as your starting ingredients. Then, on the right side, you've got the products. That's the new stuff you create. So, reactants react to produce products. Got it? Awesome.
All right, we're getting to the most important part of writing these equations. There is one golden rule that you absolutely, positively cannot break, and it's all based on a fundamental law of how the universe works.
This idea is called the law of conservation of mass. What it really means is, whatever atoms you start with, you have to end with the exact same number of those atoms. They might get shuffled around to make new things, but they can't just disappear or pop into existence out of nowhere.
So let's take a look at this reaction between iron and steam. Right now, this is what we call a skeletal equation. And if you look closely, you'll see it's totally breaking our golden rule. It's unbalanced. Let's see just how bad it is.
And this little table makes the problem super clear. On the left, the reactant side, we're starting with just one iron atom and one oxygen atom. But look at the right. On the product side, we've somehow ended up with 3 iron atoms and 4 oxygen atoms. That's just not possible. We've got to fix this.
So, how do we fix it? We balance it, step by step. First, and this is a great trick, just imagine drawing boxes around each formula. That tells you that you cannot change the little numbers inside the boxes. You can only put big numbers, we call them coefficients, out in front. Okay, next we start with the most complicated part, which is usually a good idea. We see we need 4 oxygen atoms on the left, so we put a big 4 in front of the H2O. Boom! Oxygen is balanced. But wait, that just gave us 8 hydrogen atoms on the left. No problem, we just put a 4 in front of the H2O on the right. Now hydrogen is balanced. We're so close. Finally, we see 3 iron atoms on the right, so we just need to put a 3 in front of the Fe on the left. And for the last step, we do a final check. And guess what? Everything matches. We did it!
And there you have it, a perfectly balanced chemical equation. Now, the number of atoms of iron, hydrogen, and oxygen are the same on both sides. And see those little letters in parentheses? Those just tell us the state of each substance, S for solid and G for gas. So we know the water here is actually steam.
So now that you know how to write and balance equations, we can start to see that reactions aren't just a bunch of random chaos. They actually fall into some pretty predictable patterns or types. Let's check out a couple of the big ones.
First up, we've got a combination reaction. And it's exactly what it sounds like. 2 or more things, let's call them A and B, combine to form one single new thing, AB. A perfect example is adding water to quicklime. They combine to make slaked lime, and if you ever try this, you'll feel the container get really hot because it's releasing a ton of heat. We call that an exothermic reaction.
And the opposite of a combination reaction is a decomposition reaction. This is where one single compound, AB, breaks down into two or more simpler things. A classic example is heating up ferrous sulfate. When you add heat, this one substance literally falls apart into three different simpler products. So one thing breaks down into many.
Okay, you've learned the language, you know the golden rule, and you've even seen some of the basic patterns. I think you're ready. It's time to put your new chemistry knowledge to the test with a little pop quiz.
All right, question number 1. This is a practical one. Say you're in a lab and you're about to burn a magnesium ribbon, but the instructions say you have to clean it first with sandpaper. Why is that? What's the point? And the answer is, because magnesium naturally reacts with the oxygen in the air around it. It forms this thin, tough, protective layer of magnesium oxide that's not very reactive at all. So by sanding it, you're scraping off that dull layer and exposing the fresh, super-reactive magnesium underneath.
Okay, here it is, the final challenge. Can you take this word equation and turn it into a fully balanced chemical equation? Use all those skills we just practiced. This one is a little tricky, so take your time.
And here's the answer. If you got this right, you should be seriously proud of yourself. That was not an easy one to balance. You totally nailed it. Fantastic work.
So there you have it. We've cracked the code. You can now read and write the secret language of chemistry. So my final question for you is this. As you go about your day, what everyday changes, like toast browning or a bath bomb fizzing, will you now see for what they really are? Amazing, complex, and beautifully balanced chemical reactions. Thanks so much for joining me.